Imagine descending beneath the ocean itself, a hidden roadway forged under crushing tides. Above you, millions of tons of water drift in silence, while below rests a tight fusion of steel and concrete shaped with meticulous care. It feels like something born from fiction, yet it stands as a triumph of modern engineering. The underwater tunnel. So how were such giants built? Amid relentless pressure, shifting sediments, and an isolated world untouched by daylight, humanity dared to build beneath the waves. In this film, guides you into the deep to reveal how engineers turned impossibility into reality, crafting breathtaking structures concealed far below the sea's restless surface. In our modern era, underwater tunnels reshape global movement and expand human reach. These vast structures unite regions once separated by sweeping bays, roaring rivers, or entire stretches of ocean, sparking a new age of transport and logistics. Picture crossing from island to island, or gliding under a massive bay in mere minutes. No ferries, no towering bridges, just a silent passageway carved below the waves, made possible by the unseen architecture of underwater tunnels. Beyond saving precious time, these deep passages uphold the world's flow of goods and travelers, ensuring trade moves swiftly and securely. For many nations, such tunnels act as vital lifelines of economic growth, especially for major ports, unlocking new horizons for commerce and regional expansion. Yet constructing them demands immense preparation and flawless design discipline, where every stage is calculated with absolute precision to ensure feasibility, endurance, and uncompromising safety throughout the entire undertaking. The journey begins with exhaustive surveys of the seabed. Engineers map underwater terrain, extract core samples, and study layers of rock to understand geological strength, seabed stability, and any hidden dangers that could jeopardize construction. Alongside this technical mission, environmental protections guide every decision. Teams evaluate how the tunnel may affect marine ecosystems, ensuring vulnerable species remain safe and natural habitats are disturbed as little as possible throughout planning and execution. The journey begins with exhaustive surveys of the seabed. Engineers map underwater terrain, extract core samples, and study layers of rock to understand geological strength, seabed stability, and any hidden dangers that could jeopardize construction. Alongside this technical mission, environmental protections guide every decision. Teams evaluate how the tunnel may affect marine ecosystems, ensuring vulnerable species remain safe and natural habitats are disturbed as little as possible throughout planning and execution. Each colossal tunnel unit stretches around 217 meters long and weighs beyond 73,000 tons in total mass. Engineers build these pieces with remarkable precision so that every joint fits true and no seawater can ever breach their defenses fully. Inside each one, multiple chambers serve key roles: dual highway lanes, a railway path, and a service corridor for future careful inspection and maintenance ops. Once fabrication ends, the finished units move towards seawaters and are carefully lowered into their pre-dredged place on the ocean floor using floating pontoons guided by skilled crane teams. Afterward, each giant piece connects in order to build one continuous underwater route at the desired length. The toughest part is forming each sealed joint fully. Any small flaw could let seawater rush in with heavy pressure to ruin everything. Thick rubber sealing rings are fitted between the massive tubes to guarantee total water resistance. Then layers of gravel and sand settle around the tunnel, preventing it from rising under intense underwater pressure. Only when the locking systems finish and structural firmness is achieved are the temporary steel bulkheads taken away, turning each lonely tube into a bonded tunnel system. But this approach only succeeds where the ocean floor is calm and the currents behave gently. Where fierce water motion or uneven seabed geology exists, the immersed tube strategy becomes nearly impossible. Strong turbulence and rugged terrain make it very difficult to anchor structures and maintain long-term waterproof capability effectively. In addition to submerged tube assembly, engineers employ the shield tunneling technique for other sections. Known as a tunnel boring machine, or TBM, this enormous self-contained device digs soil, removes debris, and simultaneously installs reinforced concrete tunnel linings in one continuous cycle. It functions as a closed system capable of performing excavation, transportation, and lining placement with remarkable precision and minimal environmental disturbance. This method allows tunneling beneath riverbeds and ground while maintaining exacting safety standards. At the TBM's forefront spins a cutter head nearly 12 meters across, weighing over 200 tons. Equipped with 140 high-strength steel blades and discs, it rotates slowly, exerting up to 400 bar of pressure, enough to break through solid rock and compact soil as it advances steadily beneath the surface. Excavated material is pulled into the chamber behind the cutter head, where foam and water stabilize earth pressure, critical to prevent collapses in soft or saturated ground. The slurry moves on a continuous conveyor to the surface, passes through a discharge tower, mixes with lime to lower moisture, and is finally loaded onto trucks for safe disposal, keeping operations clean, efficient, and uninterrupted during the excavation process. While excavation continues, the TBM rear section automatically installs precast concrete segments, forming each tunnel ring. Once a complete ring is in place, a grout system fills the space between the lining and surrounding soil, securing the structure and ensuring waterproofing. Hydraulic cylinders at the rear then push the machine forward, starting the next cycle of dig, install, and advance with constant monitoring to maintain perfect alignment and stability. Each cycle lasts about 90 minutes, producing 8 to 10 lining rings daily, roughly 20 meters of completed tunnel, operating around the clock. Hundreds of engineers monitor pressure, temperature, and camera feeds in real time. Thanks to its sealed, automated design, the TBM can function for months beneath the ground without interruption, embodying the peak of modern tunnel engineering and industrial precision. Yet its primary limit lies in speed when encountering extremely hard rock or irregular pressure zones. In such cases, engineers must withdraw the machine and switch to alternative methods to safely continue excavation while preserving structural integrity and avoiding delays or risks to the project. Next, engineers turn to the drill and blast technique in regions with hard rock formations or where the TBM cannot operate effectively. This traditional method, still widely used, advances in sequential cycles, drilling, controlled blasting, removing debris, supporting the excavation, and reinforcing the structure. Each step demands strict precision and adherence to safety protocols to protect both workers and the surrounding environment from the powerful forces unleashed underground. The process begins with dozens of carefully measured blast holes drilled into the tunnel face following detailed technical plans. Explosives, inserted into each borehole, are fitted with electric detonators and connected with cords arranged in precise sequences. Each detonation is timed to optimize rock fragmentation while reducing vibration and avoiding structural damage to the surface or nearby infrastructure, ensuring a controlled and safe removal of material. Before blasting, all explosives undergo testing and certification to guarantee safety. Ventilation systems are depressurized to prevent shockwave damage, and crews inspect every electrical connection and measure circuit resistance. Only once all conditions meet strict safety standards do engineers initiate the blast. The electrical signal triggers detonators, fracturing approximately 1.5 meters of rock at the tunnel face, while ensuring that the surrounding ground remains stable. After each detonation, work pauses for at least 20 minutes to allow ventilation and inspection. On average, each blast consumes 80 to 100 kilograms of explosives, with 9 to 18 blasts performed daily, depending on geological conditions and project scale. While this method is cost-effective and can advance excavation quickly, the resulting vibrations can crack surrounding structures and cause water leaks, making it unsuitable for underwater tunnel construction. Additionally, The shockwaves produced by blasting can severely affect marine life. Consequently, the drill and blast technique is largely reserved for mountain tunnels or dry terrain, where the TBM and immersed tube methods are impractical. When all three previous methods are unfeasible, engineers must revert to traditional tunneling techniques to safely continue, particularly in complex geological conditions or areas subjected to extreme water pressure. In traditional excavation, construction begins with a vertical shaft from the surface down to tunnel level. This shaft becomes the project's lifeline, transporting workers, machinery, materials, and excavated rock. Soil and rock are carefully loaded into sealed containers and hoisted to the surface using cranes. Every step is monitored meticulously to maintain safety and efficiency, ensuring that even in challenging conditions, the project can advance without compromising tunnel stability or worker security. Where blasting is prohibited or the soil is too weak, crews switch to hydraulic cutting tools to carefully slice through sediment layers. Although slower than explosives, this technique significantly reduces the risk of ground settlement and ensures tunnel stability. After each excavation stage, the newly exposed section is immediately reinforced with shotcrete, followed by the installation of steel arches, mesh, rock bolts, and anchors to prevent collapse and maintain structural integrity. Mechanical and maintenance teams operate around the clock, monitoring air pressure, equipment condition, and dewatering systems. Maintaining equilibrium between the tunnel interior and the surrounding environment is critical. Any imbalance could allow seawater to seep in, flooding entire sections. By combining classical engineering methods with modern monitoring technology, traditional excavation remains reliable for underwater tunnels in complex geology, where only precision, persistence, and deep knowledge of marine pressure can ensure safety. Once construction concludes, safety inspections and operational assessments become the priority. Many modern tunnels feature dual levels, doubling traffic capacity without increasing the footprint. Vehicles can maintain roughly 60 kilometers per hour, with emergency exits every 200 meters. Engineers perform rigorous tests, checking waterproofing, pressure resistance, fire safety, ventilation, and overall structural integrity to guarantee that every tunnel section meets stringent standards before public use. The tunnel's journey does not end when it opens. Ongoing maintenance defines longevity and safety. Dedicated teams regularly inspect concrete linings, waterproof membranes, support frames, and drainage systems to detect early signs of wear or deformation. Hundreds of sensors continuously monitor pressure, temperature, humidity, and vibration, sending real-time data to a central control center. Engineers can respond immediately to structural fatigue, ensuring the tunnel remains safe and fully operational under the immense weight of the ocean above. Cleaning and sediment removal are carried out periodically using specialized vehicles equipped with high-pressure water jets and suction systems to keep the tunnel floor clear. Combining advanced sensors with precise manual maintenance, today's underwater tunnels can operate safely, efficiently, and sustainably for decades. They withstand the extreme pressures and harsh conditions of the ocean depths, standing as enduring symbols of human resilience and engineering mastery beneath the waves. Beneath waters where sunlight barely penetrates, humanity has carved pathways of steel and intelligence. Every meter of these tunnels represents more than engineering skill. It is a monument to courage, innovation, and the relentless drive to push boundaries.